In this exercise, we are going to find the volume of a solid which is trapped between the sphere of radius 4, so the equation is x squared plus y squared plus z squared equals 16, and a paraboloid opening upwards whose equation is z equals x squared plus y squared all over 6. So the first thing we're going to do is sketch a picture of this solid. We'll talk about how to find the volume using a double integral, and then we'll do that. And then in the next exercise, we will take the same solid, but we'll write two different ways to find the volume alternatively by setting it up as a triple integral. But let's stick with this double integral so far. So let's sketch, how about the paraboloid first? So we have some paraboloid opening upwards, and then it's going to meet the sphere, which is coming downwards. So I'm going to give it like a spherical cap, like this. These two objects in three-dimensional space meet in what will be a circle. So I add my axes here. We have the z-axis, this is the y-axis, this is the x-axis, like so. My x-axis went off the screen. And the solid in particular is this region in here. Okay, so how are we going to set this up as a double integral computation? Well, we can say that the volume is going to be the double integral over some domain of integration, which I'm going to highlight in a minute, of the region trapped between these two surfaces. So the sphere is x squared plus y squared plus z squared equals 16. The paraboloid was z equals x squared plus y squared over 6. I want to think of this top one, which is currently an equation relating x, y, and z, as the graph of a function. So I'm going to switch this to z equals the square root of 16 minus x squared minus y squared. So that I can think of this upper surface here as the graph of the equation z equals f of x and y, where f of x and y is the square root of 16 minus x squared minus y squared. The lower surface, this paraboloid opening upwards, is already written as z is explicitly a function of x and y. So we will have our top function, so this square root of 16 minus x squared, minus our bottom function. And then I'm going to integrate that with respect to the variables in the domain of integration. When I write dA here, basically I mean dx dy. Okay, so what is the domain D that we're going to integrate over? Well, written this way, where we're saying that the solid is trapped between two functions where z is depending on x and y, we want to imagine kind of placing the sun right over the z-axis and shining the light straight down on this solid. The shadow that it casts in the xy plane is a solid disk. Okay, so my picture's not totally to scale, but this is the domain of integration. So I could set this up in xy coordinates, but because the domain of integration is round, it would be more natural for us to switch to cylindrical coordinates. So to actually do the setup, we're going to describe this domain of integration in terms of the radial coordinate r and the angular coordinate theta. And then we will take our integrand and translate the current expressions into cylindrical coordinates and set up dA will become r dr d theta. Okay, so what are the correct bounds for r and theta? For r, what I'm going to imagine doing is starting at the center of the disk. So we have this disk that we're integrating over. Radiate outwards until you get to the edge. The journey is the same each time. So in all cases, when we radiate outwards from the center of this disk to the edge, we're starting at a radial coordinate of 0, that is in the region of integration, and then we're ending on what's actually the shadow of this curve of intersection. So the radius of this circle, which is created when the paraboloid intersects the sphere, is what's going to determine the upper bound for our radial coordinate. So polar bounds, or cylindrical bounds. Okay. We're going to say that 0 is less than or equal to r, is less than or equal to the radius for the curve of intersection. Switch markers. I think that one got a little tired. To understand this curve of intersection, we need to realize that every point on this curve of intersection simultaneously satisfies two equations. they satisfy x squared plus y squared plus z squared equals 16 and z equals x squared plus y squared divided by 6. So I need to combine these two equations into one to see what we can say more specifically about the coordinates that live on this curve of intersection. So since I see the x squared plus y squared quantity here in this numerator, and then we also have it here, what I'm going to do is solve for x squared plus y squared in this equation, say it's equal to 6z, and then substitute that into the sphere equation. That's going to give us 6z plus z squared, equals 16. This is a quadratic equation for z, so can rearrange it. Z squared plus 6z minus 16 equals 0. This actually factors, otherwise you could use the quadratic equation. So we can say z plus 8, z minus 2, the product of those two expressions is 0. So the solutions to this algebraic equation are z equals negative 8 and z equals 2. Z equals negative 8 is way down here underneath our solid. So at the curve of intersection, all of the z coordinates are 2. Okay. Since x squared plus y squared equals 6 times that z coordinate, I didn't do a good job writing 2. There we go, 2. We can say that x squared plus y squared equals 12. So x squared plus y squared is 6 times 2, which is 12. Since this is r squared, we can say r squared equals 12 on this curve of intersection. Take the square root of both sides, and you'll get 2 square root of 3. The radial coordinate is immediate. If we think of the positive x-axis and rotating off of it, we rotate all the way around to describe this domain of integration. So the bounds on theta are from 0 to 2 pi. Like so. Now we have everything we need to set up the double integral and evaluate it to compute the volume of this solid region. So we can say the volume integrating over this disk in polar coordinates is going to be an integral from 0 to 2 pi, from 0 to 2 square root of 3, and then the top surface minus the bottom surface, or the top function minus the bottom function. So again, here's the top, here's the bottom. In cylindrical coordinates, minus x squared minus y squared is minus r squared. So the top is the square root of 16 minus r squared. And then the bottom is going to be r squared divided by 6. Let me put this in parentheses. And then what I wrote here is dA. When I switch that to polar coordinates, it's going to be r dr d theta. What you could do here is integrate everything with respect to r, plug in the top and bottom bounds for r, and then integrate everything with respect to theta. Since I have a double integral over constant bounds, and in my integrand I only see r dependence, I don't see any theta dependence, this factors into the product of two single integrals. You don't have to do it this way, but I like taking this kind of expression and rewriting it as the integral from 0 to 2 pi 1 d theta times the integral from 0 to 2 square root of 3. And then I'm going to group this as r times the square root of 16 minus r squared, and then minus r cubed over 6 dr. Okay, you don't have to split this double integral into the product of two single integrals. You can iterate in the usual way. When I do this though, that first integral is just going to immediately return me 2 pi minus 0. For this other part, the first expression is going to be a u sub. So 16 minus r squared, if I take the derivative of that, I get negative 2r, and I see that r hanging out here. So if I let u equal 16 minus r squared, du is negative 2r dr. So I'm only going to do that u substitution on the first one. That means I'm going to take what's currently one integral with respect to r and write it as 2. I'm going to break it up across the subtraction. Square root of 16 minus r squared is going to become square root of u. And then r dr is going to be negative 1/2 du. So I've converted the integrand from r to u. Let me also convert the bounds. When r is 0, u is 16 minus 0 squared. So that's 16. When r is 2 square root of 3, or square root of 12, 16 is, u is 16 minus that squared, so 16 minus 12 is 4. So that's my first integral after the conversion with u substitution. The second one, let me just rewrite it as the integral from 0 to 2 square root of 3 r cubed over 6. This is just going to be regular power rule anti-differentiation. Now let's evaluate these two remaining integrals. I'm going to actually factor a negative 1/2 out front. I hope that's not going to lead to an algebra mistake. Proceed with caution if you do this kind of thing. So the negative 1/2 is going to come out and leave me with negative pi times, now I'm just looking at the integral of the square root of u. So that's u to the 1/2 power. The antiderivative of that is u to the 3/2. But I need that to cancel out, so I'll have a leading term of 2/3. We will plug in 16 and 4. And then I pulled a negative 1/2 out front, so it's going to be plus, and then I'm left with r cubed over 3. So that's going to be r to the 4th over 12. So that the 4 comes down, 4 over 12 is the remaining 1/3. We'll put in 0 and 2 square root of 3. Okay, we just need to evaluate this now. So we have that leading negative pi out front, 2/3. And then what is 4 to the 3/2? Well, 4 to the 1/2 is like, what's the square root of 4? So that's 2. Cube it, you get 8. 2/3 times 8 minus, same thing here. 16 to the 3/2 is 16 to the 1/2 cubed. 16 to the 1/2 is 4. Cube it, you get 64. Okay. And then for the second expression, we need to take 2 square root of 3 and raise it to the 4th power. Squared is 12. Square that again, you get 144. Divide that by 12, and you're left with 12. I think I will leave this here now because it's just a question of algebra, and that's something I'm never quite good at doing on my feet. So this is, at this point, the final answer. So this would be the volume enclosed between this paraboloid and this sphere. And given that we're about to solve this again, but with triple integrals, what I want you to take out of this demonstration is how to take a volume question and interpret it correctly with a double integral. So you're double integrating over a two-dimensional domain. For us, that's the shadow cast down in the xy plane. So we've described that disk using cylindrical coordinates. And then what is the integrand when you do a volume computation as a double integral? You have to look at volume enclosed under the graph of a function. So here I have volume enclosed between this top function, the sphere, and the bottom function, the paraboloid. It's analogous to something you probably saw in single variable calculus when you looked at the area between two curves and you were integrating f of x minus g of x or something like that. Same idea here. So it's top function minus bottom function. Now we're going to compute the same volume that we just did with the double integral, but this time I'm going to just set up and not evaluate two triple integrals. One in cylindrical coordinates, that's not going to be very different from what we just did, and then the second one will be in spherical coordinates. Okay, so here's the picture of the solid whose volume we're trying to compute. It's enclosed between the graph of z equals x squared plus y squared over 6 and the graph of z equals the square root of 16 minus x squared minus y squared. In cylindrical coordinates, we already saw that the bounds on the radial coordinate go from 0 to 2 square root of 3, and the bounds on the angular coordinate go from 0 to 2 pi. If we're going to set this up as a triple integral, I also need bounds on the z coordinate. So we've got x and y described in a polar way using r and theta. For z, you want to imagine coming anywhere in the domain for x and y, traveling upwards. When you describe the z bounds here, you want to think, when do you enter the region for z, and when do you exit the region? So I enter here and I exit here. If I come over here, this point in the domain, I enter here and I exit here. Notice the range of z values here is different depending on where I am in my domain, which means that the bounds I give for z must adjust themselves to different choices of x and y. I'm saying this because sometimes I see students want to return the bounds for z as 0 to 4 in this case, because they say the smallest value for z is 0 and the largest value is 4. But if you say that z is between 0 and 4, that suggests that the bounds for z are 0 to 4 all over the domain. So if I'm out here, we would already be in the solid whose volume we want right now, right on the disk, all the way up to this height. And that's just not accurate. So you need to make sure that your bounds for z reflect the fact that z is being determined by functions of x and y. So the bounds for z are going to be r squared over 6, where I've converted this equation to cylindrical coordinates. That's determining when we enter the solid, up through this equation that determines when we exit the solid. So that's 16 minus r squared. So you must have bounds which reflect the fact that this solid has a shape, and the shape is being determined by these two functions. The volume is now the triple integral over this solid S of 1 dv. Conceptually, that's what we're going to triple integrate. So the integrand is 1. dv here is the appropriate choice of differentials. So you could think of it as dx, dy, dz, but we're going to write them in cylindrical coordinates, so we'll pick up an r. And then S is this region whose bounds we've just written down. So I'm just going to set this up. We can say that the bounds are going to go from 0 to 2 pi for theta, 0 to 2 square root of 3 for r, and then r squared over 6 to the square root of 16 minus r squared for z. The integrand is 1, and then dv with cylindrical coordinates needs to be r dz dr d theta, like that. One thing you have to be careful about here is that because your z bounds depend on r, the z integration needs to happen inside relative to r. So you have to have dz before dr so that these bounds are going to be evaluated before the bounds on r. Otherwise, you're ready to go. And what will happen if you actually work this out and you have the work that we just did on the first exercise handy is what you'll discover is after one round of integration here, you'll return back the double integral that we just saw. So that's how you can see the link between that double integral calculation we did with cylindrical coordinates and this triple integral with cylindrical coordinates. Okay, with spherical coordinates, we have our same notion of theta that we have with cylindrical coordinates. But now we also have an angle phi, which measures rotation down from the positive z-axis, as well as a radial coordinate rho, which is the radius coming out in any direction from the origin. So I think what we're going to need to do is to break this into two regions, because as long as I'm kind of under the spherical cap, like if I'm rotating down from the positive z-axis, what we get is a solid spherical region all the way until we reach this curve of intersection, and then it changes. So in what's ultimately going to be the region inside of a cone, under the spherical cap, we have that theta goes from 0 to 2 pi. In fact, that's consistent throughout the domain. Phi is going to rotate from the positive z-axis to this curve of intersection. So we let phi just drop down like that. And then rho, the radial coordinate, starts at the origin and goes out to 4. So it's consistently from 0 to 4 everywhere on the inside of what's going to be like a cone region inside this solid. However, once we get out here, then what's going to happen is that our radial coordinate rho gets chopped off as we rotate down. So right on this curve of intersection, it's still going from 0 to 4. But then as we let phi rotate down, down, down to pi over 2, so overall phi is going to swing us down to the xy plane, the rho coordinate upper bound gets shorter and shorter. It's actually going to get down to 0 right on the xy plane. So in this region, rho is going to be a function of phi. Okay, so let me call this region 1 and region 2. Region 1 is not too bad at all. What we mainly need to figure out is the phi value at this point of intersection. So we start at phi equals 0, r and theta, or rather rho and theta are constants, and phi is just going to drop us down to that curve of intersection. So what is this? We need to find phi here. That's going to be the dividing line between R1 and R2, the two regions inside of this solid. For that, let's take our equations and just convert them to spherical coordinates. I think the first one's not going to be too interesting because x squared plus y squared plus z squared equals 16, and spherical coordinates is just rho squared equals 16, so we don't get too much from that. But what is happening is that at this moment that we've rotated, we've kind of passed over to the paraboloid. So if I take z equals x squared plus y squared divided by 6 and convert all of that into spherical coordinates, we'll end up with an equation that we can solve for phi. So bear with me here. What I'm going to do is take the z, the x, and the y and just convert them to spherical coordinates. So for z, we're going to have rho cosine phi. For x squared plus y squared, if you write down x is rho cosine theta sine phi, y is rho sine theta sine phi, and square them and add them together, the thetas will combine to 1. What I'm trying to say there is that x squared plus y squared in spherical coordinates is rho squared sine squared phi, and then all over 6. Okay, so that's always x squared plus y squared in spherical coordinates. It's rho squared sine squared phi. Let me cancel out one copy of rho and I'll bring the 6 over. So we have 6 cosine phi equals rho sine squared phi. At the moment that these two surfaces intersect, yes, it's true that this relationship is holding because this is for the paraboloid, but it's also true that we're on the sphere, which means rho equals 4. So on the curve of intersection, rho is 4. So I'm going to plug 4 into that. 6 cosine phi is 4. And then I've got mixed trig functions here. I have cosine and sine. Sine squared is 1 minus cosine squared phi. And then this gives me a quadratic equation for cosine. So we can say, I'm going to try to do something a little dangerous here. I'm going to distribute, bring over, and divide everything by 2 at the same time. So that's going to be 2 cosine squared phi plus 3 cosine phi minus 2 equals 0. You can use the quadratic equation on this. I think it actually factors. Let me just give it one good try at factoring, and if I can't do it, we'll switch to the quadratic equation. So this is quadratic in cosine, which means that, like, if you think of a quadratic equation as 2x squared plus 3x minus 2, we're going to treat cosine theta, or cosine phi, exactly as we would treat x in a regular looking quadratic equation. So I'm going to have 2 cosine phi, so that gives me back the 2 cosine squared, plus 2 minus 1. Oh, I wrote minus 4, but I should have written minus 1. Okay, so that's 2 cosine squared plus 4 cosine minus cosine is 3 cosine minus 2. So actually it did factor. This second one would give us a solution that cannot happen. This would say cosine phi is negative 2, but cosine values are always between 1 and negative 1. So this is not a real solution. So cosine phi is 1/2. Let me write that here. Cosine phi is 1/2, which means that phi is pi over 3. Okay, so right here, by the moment that we've rotated down to this curve of intersection, phi has gone from 0 to pi over 3. All right. That means that for the rest of the region, this kind of wedge shape that's a little bit trickier to describe, phi is going to go from pi over 3 to pi over 2. So those will be the bounds for phi, from pi over 3 to pi over 2. What remains is to figure out how rho depends on phi in this trickier region. So we have to kind of draw a triangle, I think, and try to set up some ratio using trig that's going to relate rho to phi. I would like to draw a triangle where you can really see what's going on. So let me kind of erase some of these lines so that we can put a triangle inside of this region. Here's how we are going to relate rho to phi. I'm going to imagine I have a point on the edge of this paraboloid. Connect it to the origin. The length of this line segment is our rho. That's what we're looking to describe. How much have I rotated at that point is phi. This would be some number between pi over 3 and pi over 2. I've got an angle, I've got an edge. I would love to have a right triangle. So let me bring this line segment straight over to the z-axis so that this is a right angle here. This height is z. All right, so I've got the height of z, hypotenuse of rho, and then if I wanted to, I could find this third side. I don't think we will need it, but you could find it using the Pythagorean theorem. This angle right here is phi. Let's set up a ratio. We have the adjacent side and the hypotenuse. So in R2, let me erase the spherical coordinates remark. That's what we're doing. Okay, so in this second region, which I'm calling R2, this trickier region, we have the relationship that cosine of phi is adjacent over hypotenuse. That's z over rho. Careful here. If you plug in z equals rho cosine phi, your rho's will cancel and you'll get cosine phi equals cosine phi. And you'll think that, hey, that wasn't very useful. But what is determining z here? Z is on the paraboloid x squared plus y squared over 6. So instead of just calling this z and doing a conversion that leads to just a generically true statement, let's take that z now and replace it by x squared plus y squared over 6. All right, x squared plus y squared over 6 rho. So how about I bring the 6 over, 6 cosine phi, and then x squared plus y squared, I already said what that was. It's always rho squared sine squared phi. So rho squared sine squared phi all over rho is rho sine squared phi. Okay, so here is a relationship between rho and phi. I can bring the sine squared over and say that if I'm somewhere in this second region where the cutoff is by this paraboloid rather than the nice sphere, the rho, the distance that we go from the origin outwards to the edge of our region, is given in terms of phi via the relationship rho equals 6 cosine phi divided by sine squared phi. It's pretty tricky to get there. It's a multi-step process, and if you're watching this, you're like, why don't you just do cylindrical coordinates? And I definitely would for this problem, but it's a nice exercise. We have everything now that we need to set up this volume. Because we're going to change our description along that ray that met the curve of intersection, I'm going to set up 2 volume computations. So we can now say that the volume of this region, I'll do the R1 first. For theta, it's 0 to 2 pi. For phi, it's 0 to pi over 3. And then for rho, in this region, it was always 0 to the edge, 0 to the edge. And the edge is the equation rho equals 4. So it's 0 to 4. It's a 4. The integrand is 1 because we're doing a triple integral to compute a volume. So the integrand function by default is 1. But then we need to pick up rho squared sine phi. That's the conversion from rectangular to spherical coordinates. And then the way I ordered this, it's d rho, d phi, d theta. Okay, so this is like the R1 computation. That's the one that was a little easier to describe, or a lot easier to describe. Add to that the integral from 0 to 2 pi for theta. For phi, again, we're rotating from pi over 3 all the way down to the xy plane because we do get tangent down here to the xy plane. So that's going to be pi over 3 to pi over 2. And then for rho, we start at the origin and we go out to a function of phi that we found. So it's going to go from 0 to 6 cosine phi over sine squared phi. Okay, so those are the bounds. The integrand is the same. I hope I can squeeze it in here. It's going to be rho squared sine phi, just like in the other one. D rho d phi d theta. Okay, sorry about squeezing that all the way over on the right. But the integrand itself it's the same rationale behind why those are what they are. This part was tricky in spherical coordinates. Spherical coordinates are great for spheres, obviously. They're also good for cones. Like I said, that nice region was actually the region inside of a cone with a spherical cap. So spheres and cones are kind of natural with spherical coordinates. This paraboloid was harder. We had to work out how rho changed as we moved through this paraboloid, and then we described our motion using the angle coordinate phi. Last remark to make here is that because rho is a function of phi, rho needs to be inside relative to phi. So I had to put d rho before d phi when I ordered my differentials there and set up my bounds accordingly.